Welcome to this course, Quick Start to Wolfram SystemModeler. My name is Mikael Forsgren and I'm an applications engineer at Wolfram Math Core. In this course, I will give a hands-on presentation how to get started with Wolfram SystemModeler. I will start by showing how you can create ready-made models. After this, I will continue by developing a model of an electric kettle using drag and drop of classes from the built-in model libraries. And at the end, I will show you where you can find more learning material. After this course, you should have a good understanding on how you can use SystemModeler to develop and simulate your own models. When you start SystemModeler for the first time, you will see the welcome screen, from which you can find introductory videos on modeling, simulation, and analysis. Here you can also access the Getting Started tutorials, the documentation center, and industry examples, as well as other resources. Just as the name indicates, Getting Started is a good place to start learning SystemModeler. So let's go ahead and click on that button. Here you will find a collection of example-driven tutorials in which you will learn about key concepts in SystemModeler. For example, how to create models textually, as shown by the Hello World example, component-based modeling, as illustrated by an electric circuit, or how to build hierarchical models, which is exemplified by a tank system. These tutorials contain step-by-step instructions from which you can learn how to develop your own system models in many different domains. All the models that are used in the Getting Started tutorials can also be found in the introductory examples package, which you can find in the class browser. The class browser contains 4 sections. The first one contains the examples packages, followed by the libraries, then comes the user classes, and finally the recently used classes. You can open and navigate to different packages and classes by clicking on the arrow. Let's expand the systems package and open a model of an inverted pendulum. And I open it by double-clicking on the model. As you can see, this model consists of a controller, a motor, a gear, and a pendulum. If I select any component, for example the motor, we can see its parameters at the bottom of the screen. For instance, the resistance. You can also double-click on any component to see how it's designed. Here we have, for example, a resistor, inductor, and electromotoric force. And just as before, I can select any of these to learn more about the specific component. Let's go ahead and simulate this model. I start by going back to the top level by clicking up, and start the simulation by using this play button. Now the simulation center opens and an experiment is created with our model. In the experiment browser, we can access all components in our model: the controller, the gear, the motor, and the pendulum. Let's expand the motor component and plot the voltage. In the plot window, we can now see the dynamics of the motor voltage, local minima and maxima. If you would like to change the appearance of the figure, this can easily be done by clicking on the Plot Theme button. And you have a wide variety of different themes to choose from. Since this is a 3D mechanical system, we can also get an animation on our pendulum. This animation can be seen by clicking on the Animation button. An animation window is opened, and the animation is started by clicking on the Play button. You can zoom in or out by using the scroll wheel. You can control how the animation is played. For example, you can set it to play continuously, as well as set the animation to play fast or slow. The animation feature is a good way to further understand how the system behaves. Another smart feature is that if you click on any component in the animation, for example the box, this component will be opened in the Plot tab. And if I click on the cylinder, we will see all the variables that might be of interest to plot instead. I have now shown how to use ready-made models by simulating it and studying its behavior. Now let's go ahead and start building our first model by using drag and drop. The model that we shall now create is a model of an electric kettle. It's a simple and small system which will illustrate SystemModeler's multi-engineering capabilities. We will use components from the electrical and thermal domains as well as regulators. We can locate the needed components in the Modelica standard library, which is shipped with the software. However, before we start assembling our system, we need to create a new model. So I go to the new class icon in the toolbar, click on it, and choose the appropriate class. In this case, a model. I type in a suitable name, electric kettle, and finally I add a description of my model. Then I simply press OK to create the model. Now that the model has been created, we can see that we have an empty diagram view representing the model, with the name electric kettle on top. And this model can now also be found in the user classes section of the class browser. We will start by assembling the electric circuit in our model. So I navigate to Electrical, Analog, Basic, click on the ground class and hold down the mouse button. Drag the class to the diagram view and release the mouse button. I'll now perform the same procedure for the resistor. And if you want to change the orientation of your components, you can do this easily by right-clicking on the component. Choose Shape and Rotate Right. There is also a handy shortcut, Ctrl-R, to perform the same task. I will use a voltage source as an input to my model. This class can be found on the Analog Sources package. And as you can see, there are many different sources. For example, ramp voltage and sawtooth voltage. For our model, I will pick the sine voltage and rotate the component on the diagram. Next, I navigate to the Analog Ideal package and locate the ideal closing switch. And with the final piece added to the electric circuit, I am ready to connect my components together. You can connect components in SystemModeler using the Connection Line tool. Move the cursor to the connector that you want to connect. Notice how the cursor changes shape. Click once and move the cursor to the other connector you want to connect with, and click again. I perform the same task in order to complete the electric circuit. It is now time to add the thermal components to the electric kettle. These classes can be found in the thermal library in the Modelica standard library. So let's navigate to Thermal, Heat Transfer, Components. I will use the heat capacitor to model the water in the kettle. I add the component to the diagram layer, just as before. But for this component, I think a name change would be suitable. So I right-click on the component, choose Rename, and I will give it the name Water, and then just click OK. And as you can see, we have now changed the name of that component. Let's connect the water component to the resistor, which is our heating element. However, if I try this operation, SystemModeler won't allow it. This is because the connectors are of different types. One is from the electrical domain, while the other is from the thermal domain. So how can I connect the two different components? Start by aborting the connect action, and then select the resistor. At the bottom of the screen, there's a parameter called Use Heat Port, and I set that parameter to True. We can now see that the heat port has been added to the resistor. I just flip the resistor and can now connect the water and the resistor components to each other. I also want to model the heat loss, and I assume that most of the heat loss is due to radiation, so I will use the body radiation class for this. I drag the class to the diagram view, rotate it, and then connect it to the water. In order to model the ambient temperature, I'll use a fixed input temperature. This can be done by using a heat source. I'll use the Celsius package since I prefer Celsius over Kelvin. The thermal part of the model is now ready. Now we only need a regulator to control the electric circuit. First, we need to know the temperature of the water in order to regulate the heater. So I'll add a temperature sensor. Next, I navigate to the blocks, logic package, in order to find a class that can be used to turn on or off the heating element. Here we can find the on-off controller, which seems suitable. Let's go to the documentation and learn more about this class. Here you can see the description of the class, learn about its connectors, parameters, and also find examples in which this class is used. Let's open the controlled temperature example to learn how we can use this class. Just as on the documentation page of the controller, the examples comes with general information as well as a list of parameters and other components used within this example. At the top of the page, we also see a diagram view, which actually resembles our model. If I click on the name of the example at the top of the documentation center and then go back to the model center, we can explore this example even further. It looks like this controller performs the task we need in our model, so it seems like a good idea to use the on-off controller. I will also need a reference signal for the controller that tells the controller how hot we want the water to be, and I'll use a constant source for this purpose. This is found in the blocks source package, and as soon as I've connected the on-off controller to the ideal closing switch, I have completed the system. But before we can simulate it, we need some realistic parameter values. In Sweden, where I live, the electric grid has a voltage of 230 volts and a frequency of 50 Hz. So I'm going to use this in my model. The ambient indoor temperature is typically 21 degrees Celsius, which corresponds to roughly 70 degrees Fahrenheit. Now I want to heat the water in the kettle to about 99 degrees Celsius. So let's set the reference signal to 99, and this corresponds to around 210 degrees Fahrenheit. As I don't want the switch to flip on and off as soon as the water temperature passes 99 degrees, I set the bandwidth for the controller. Here I'll use 1 degree. Suppose we want to heat 1 liter of water. Then the corresponding heat capacity will be 4180 joules per Kelvin. And I now define the surface area of the kettle to 0.15 cubic meters. And finally, I set the resistance to 16.3 ohms, corresponding to the electric kettle in our office. All parameters are now set, and before simulating, I validate that the model is correct. I can do this easily by clicking the Validate Class button. And we can now see that the model has validated successfully. Now we are ready to simulate our model. You might remember that when I simulated the inverted pendulum, the simulation was created directly after I clicked the play button. However, since we do not have any experimental settings for this model yet, we are now asked to review these prior to running the simulation. Either we use the standard settings, or we modify some of them. As you can see, there are many settings. For example, numerical tolerance, solver, and step size. I'll just increase the stop time, since 10 seconds is not long enough in order to heat up the water in the kettle. 300 seconds should be sufficient. I'll now click OK, and the model is built and simulated. I create a new plot window, and then locate the variable I want to plot, the temperature of the water. We can now see that the temperature is steadily increasing in the beginning. It starts at 293 kelvins, and then after 210 seconds it reaches 372 kelvins. After this, the water temperature drops down 1 degree at 250 seconds. If we now want to correlate the temperature curve with the on-off switch, we can just add a subplot. I click on New Subplot and locate the on-off controller in the Plot tab and select its output value. We can now see that the controller is on until the water reaches its target temperature. Then it's switched off and back on again to reheat the water to the desired temperature. This can more easily be seen if I zoom in a bit. So I click and select the area I want to see in the plot window and then release the mouse button. Notice that the upper plot also zooms in corresponding to my selection. But what if I have a different scenario? For instance, less water in the kettle. Let's use half a liter of water instead of 1 liter. To do this, I change the heat capacity in the parameters tab in my experiment. And I simulate the experiment again. We can now see that with less water in the kettle, the heater is turned on more often than our previous experiment. And as expected, it goes much faster to heat up the water when the volume is smaller. Once again, the controller keeps the temperature around our target temperature. But what if I would like to compare these two scenarios? An efficient way to achieve this is to duplicate the experiment. And just as before, I go to the Parameters tab, but now in the new experiment. As you can see, the name of the water component is shown in boldface. This means that a parameter value in this component has been changed compared to the original model. When I open the component, we can see that there's a small arrow next to the parameter value. Clicking on this arrow resets the parameter to its original value. I now simulate the experiment, so that we can compare these two scenarios. Notice that we have gotten a few suggested variables to plot, shown here in blue. One of these is the temperature of the water, as we have plotted this before in the other experiment. So I click on the variable name, and we can now see the two temperature curves in the same plot window. This way it's easy to compare different scenarios and see how things changes. Likewise, I can also compare the behavior of the on-off controller. We have now gone through how to model and simulate in SystemModeler, whether you're simulating a car, a robot, or the insulin signaling pathway. The modeling process is similar, but of course there is always more to learn. So before we end this course, let's take a look at the documentation center found within the help menu. This is a hub where you can find all sorts of useful resources to learn more about SystemModeler. Not only about the software, but also specific libraries and language concepts. You might want to start by going through the Getting Started section, in which you will find more videos and textual tutorials. These range from basic to advanced topics, and they include advice on different aspects of the modeling language, libraries, and the software. In the blue sections we find the documentation and examples for different libraries. For example, the selection of mechanical libraries. We can also explore the industry examples for more applied uses of SystemModeler. Here you can find examples in different domains, for example, industrial manufacturing and life sciences. There is also a rich source of learning material about the Modelica language itself. Modelica is the name of the modeling language used behind the scenes of all classes we have used today. The more advanced user often creates new custom classes textually by using the Modelica modeling language. So if you want to customize or create your own classes, it's wise to start by learning more about this language. For this reason, we have included a complete book of the Modelica language in SystemModeler. This is a step-by-step example-driven book covering the entire Modelica language. And as you go through an example, you will see that there is ample description on how you create and analyze such a model, as well as details on important aspects and features of the Modelica language. In this course, you have now learned the basics of SystemModeler, how to run existing models, and how to develop and simulate your own models. There are many other on-demand courses available in which you can get a more in-depth knowledge on different topics. And with that being said, I thank you very much for your attention.